Well, that's probably about 17.5. Zoop. And triangle TUV looks something... Nope. Let's call them X, just for fun. A classic. And that's that. That's your lesson. Blah, 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 blah. Welcome. We're going to look at the last lesson in chapter 10, 10-6. And I'll be honest with you guys, I don't have a lot of passion for this lesson. Geometry in general is not really my thing. Don't love it. Some days you're the garbage man and other days you're the garbage truck. Do garbage men and garbage trucks have adversarial relationships? Anyway, we're going to walk through some examples right now on similar triangles. And obviously we got some check your progress problems that we need to work out if my camera will ever cooperate. First of all, similarity has to do with proportionality, basically. So there are two different words we can use in geometry when things are in some sense equal. And I say in some sense because equality is not really a property that geometrical objects have. So we want to be very careful about saying what kinds of things are equal when we're talking about geometry. For example, angles are not equal. I could have this angle here, let's say, and I'm even going to put a little symbol there, and then I could have this angle over here and put a little symbol there, and those angles are not equal. The angles are objects, and objects are not the kind of thing that are equal. Quantities are equal. These angles, we would say, are congruent. Congruent is the geometrical word where we would normally say equality in algebra, congruence. We can say that the measure of these angles are equal. Each of these is a 90-degree angle, right? So the measure, let's call this one A, B, C, and this one we'll call D, E, F. Angle A, B, C, we can say is congruent to angle D, E, F. That's the symbol for congruence. It has that little squiggly on top. But then we could also say the measure of angle A, B, C is equal to the measure of angle D, E, F. Because, of course, 90 degrees equals 90 degrees. And so as long as it's a number or a quantity, yes, we can say equality. If it's an object, we typically want to say congruence. But even then, we would only say congruent if they were absolutely the same in nearly every respect. We can rotate them, we can flip them around, we can move them up and down or left and right, and that's fine. We can still say congruence with all of that. But as soon as we start to do this, right, as soon as we start to zoom in or out, the objects change size. We would no longer say they're congruent. That may seem obvious to you. But we also wouldn't just say, oh, well, they have nothing to do with each other anymore, right? Like clearly as I zoom in and out on these objects, you still get a sense that there is a relationship. It doesn't completely change as I make DEF larger. You can still tell that it's the same object. I'm just kind of zooming in on it. That zooming in quality is what we name similarity. So that's what we're looking at here. Similar objects are objects that maintain, in some sense, the same proportions. They maintain the same angle relationships, but they might be changing size. Specifically with the case of triangles, you can see some definitions here. Similar triangles have the same shape, but not necessarily the same size. There are two main tests. If the angles of one triangle and the corresponding angles of a second triangle have equal measures, notice measures, equality, then the triangles are similar. Or we can also say that if the measures of the sides of the two triangles form equal ratios, also known as proportionality, then the two triangles are similar. And that's summarized at the bottom of page 552. So let's just take a quick look at the example that they give. We've got this triangle ABC. I'll see if I can draw a decent ABC. That's not bad. I'm actually going to demonstrate one of the amazing things you can do with similarity right now. And I'm going to take this and just paste it over here, but change its size. I can make it bigger. And then, of course, we want to erase a few things. But the things that we can't erase are the things that maintain the similarity. The angle measures themselves cannot change. We can rename this D, E, F. We can double it in size, which is what it looks like they've done, or in some sense doubled it. We've doubled the lengths. 4 centimeters, 5 centimeters, 6 centimeters, but we can't otherwise change it. We can't change the angles themselves. We can't make it so that the sides are not proportional. What we would say in this case is triangle ABC is similar to triangle DEF. And the order does matter there. We want the given corners or given angles that have equal measure or that are congruent to make sure that they're lined up. So you can see here angle A and angle D both measure 56 degrees. It's not important that they're in the same position because, again, I could take this DEF figure and I could just as easily rotate it around, right? And I could even flip it around. Will this let me flip it? I can't get this to flip it. But it's not the fact that they're in the same position, it's that they have the same measure. So D and A have to correspond to each other. B and E have to correspond to each other. They're both 83 degrees. C and F, both 41 degrees, have to correspond to each other. So that statement of similarity ends up being really important. As soon as I see this statement of similarity, I can immediately start saying, oh, so angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. So again, similarity automatically implies congruent angles or equal angle measures. Those are the same concepts. But again, it also implies proportionality. So I can look at some of these. I can say, well, AB and DE have to be proportional to each other. So AB and DE will form a certain ratio, and that ratio needs to match, say, BC and EF's ratio. And that ratio needs to match, say, AC and DF's ratio. So you can see all of this at the bottom of page 552. This is what it means when we say that two triangles are similar. This is an if and only if situation, which just means you can also go the other direction here. If you can demonstrate that the angles are congruent and that the sides are proportional, that means you have similar triangles. But you could just as easily start with similar triangles, and that would automatically mean you have congruent angles and proportional side lengths. So that's what we're going to try and do on number 1. We don't know yet whether these triangles are similar. We're going to try and demonstrate their similarity right now. So let's jump in and see how we could demonstrate that similarity. So we have these two, and we can see PRQ with angle measures of 51 degrees and 51 degrees at R and Q. And then this triangle over here, MNO, has congruent markers at angles N and O and a 78 degree angle. And again, our job here is to demonstrate that they are in fact similar triangles. So one thing we could do is looking at triangle PRQ, we could say, well, we know that at the sum of our three angles, so that's the 51 degrees, the 51 degrees, and whatever the measure of angle P is, have to add up to 180 degrees. That's true of all triangles, right? The sum of the three interior angles of any triangle will always be, the measures, I should say, will always be 180 degrees. So 102 plus the measure of angle P equals 180. Subtract 102, subtract 102, and of course we get that the measure of angle P is equal to 78 degrees. Now that's important because as I look over at this other triangle, I see a 78 degree angle. Now it's not good enough to have just a single angle in common. We need more than one angle in common. Fortunately, because we have these congruent markers, we're going to be able to find those other two angles. In this case, we could say 78 degrees plus the measure of angle N plus the measure of angle O equals 180 degrees. But again, we know that the measure of angle N and the measure of angle O are the same thing. Let's call them X, just for fun. A classic. So if this is X and this is X, we can say 78 plus 2X equals 180. Subtract 78, subtract 78. 2X equals 102. Divide by 2, divide by 2. X equals 51. So coming back into our figure here, that's 51 degrees, that's 51 degrees. And now we can say, okay, these are in fact similar triangles. All three angles share measures with the three angles of the other triangle. They have to be similar to each other. From here, we want to write the statement of congruence. So what that looks like, oh, I forgot to come up here, right, 78, is we just want to make sure they line up. So let's actually take this triangle right here, and this would be a place where I might go ahead and rotate it such that I get the positioning right. And so I can see, oh, okay, so R is in the same position as O, and P is in the same position as M, and Q is in the same position as N. And so then I want to write my statement, triangle, let's go from the top, P, Q, R, is similar to triangle, what went with P, M, what went with Q, N, what goes with R, O. And again, I can see Q and N, P and M, R and O in that statement of similarity. This would also lead us to our different proportions if we needed them. So all of this becomes true once we demonstrate similarity. Or again, we can demonstrate the congruent angles to get similarity, or demonstrate the proportionality to get similarity. It works either way. Take a moment and work out check your progress number 1. Okay, so you can see in this case, I kind of belabored it a little bit. You could probably tell pretty early on, yes, these two triangles are definitely similar to each other. Their angles are congruent. They're both isosceles triangles with the same angles. If we needed to, we could demonstrate the proportionality of their sides as well. And that's that. That's all you have to do to show that your triangles are similar. So let's talk about what you can use similarity for, particularly as you move on to, say, geometry next year. So this is example 2. And we're told right away they're similar, so let's go ahead and get another copy down. But again, the most important thing here is contained in the problem. Example 2a states, triangle TUV is similar to triangle WXY. And again, one of the things that means is we don't even have to waste our time figuring out from our 180 degree total the different angle relationships. We can just immediately take advantage of the statement of similarity. It must be the case that angle T is congruent to angle W. It must be the case that angle U is congruent to angle X. It must be the case that angle V is congruent to angle Y. So since we already know that angle Y is 35 degrees, we can go ahead and put that in for triangle TUV. It's not super important though, because what we actually want to know are the proportionality relationships. TU compared to WX must be the same thing as UV compared to XY, must be the same thing as TV compared to WY. So if we fill this in with the actual side lengths that we know about, we can say, well, TU was 3, WXA, UV 4, XY 16. So obviously my figures here are not drawn to scale, but in my defense, neither are the books. TV is length 6, WY is length B. And so we want to solve for A and B. You can tell we can do a lot of cross products if need be. 48 equals 4A. A must be 12. But there's something a lot simpler we can do here. Take a look at this relationship right here. 4 to 16, right? How do I get from 4 to 16? Well, I must be getting 4 times bigger from the top of my fraction to the bottom of my fraction. So 6 times 4 means B has to be 24. 3 times 4, as we've already discovered, means A has to be 12. And so that's that. We can say that the side lengths are 12 for, or rather the variable A equals 12, the side length is WX, and the variable B, which corresponds to the length of WY, is going to be 24. Now that was just part A. What else do they want us to do? They just give us an example 2B. Kind of an interesting figure. This is something that's definitely going to pop up again and again. We have a right triangle, and in that right triangle are some different lengths. So we can label, we've got A, B, C, D, and E. We've got this length here is 6, though the total length is 9. We've got this length here is 10, this unknown length, X, and then we've got total hypotenuse here of Y. Well, it barely even looks like 2 triangles, or perhaps you didn't even see it as 2 triangles until I mentioned that, but it is in fact 2 triangles, right? We've got this triangle right here, triangle ABE, and then we've got the triangle that it's contained in, ACD. And what you might notice about these triangles is obviously angle A is congruent to itself, but because this is a right angle, and this is also a right angle, because both of these are given in the figure, we can also say angle E is congruent to angle D. They're both given in the figure as right angles. And if 2 angles in these triangles are congruent, you could do the whole 180 thing, and I promise you, you could eventually figure out that angle B and angle C are also going to be congruent to each other. So in fact, it's not just that this is kind of a tricky figure with two triangles, but it's also that those two triangles must be similar to each other. Let's go ahead and write our statement of similarity. We can say triangle ABE is similar to triangle ACD. And again, what I'm watching for when I do that is I'm making sure, of course, A is congruent to itself, B is congruent to C, which we figured out, and as the figure gave us, E is congruent to D. Once I have a similarity, I can go ahead and write my proportions down. A to B must be proportional to AC. BE must be proportional to CD. And of course, AE must be proportional to AD. As I start to fill in what I already know, AB is an unknown. It doesn't have a variable, so let's just give it a question mark. AC, they're calling Y. BE is 10. CD, they called X. And then AE is 6. And AD is 9. And that's the key. We need some proportion along the way that we actually know. We're going from 6 to 9. Now you could say, well, that's times 1.5, but perhaps you didn't see that directly. So again, we can just immediately go for cross multiplication. 90 equals 6 times x, divide by 6, divide by 6. X must be 15. So this side length right here is going to be equal to 15. How much did they want us to find? Just both x and y? Okay, x is 15. If they only want us to find y at this point, you might notice y was in a relationship with a question mark, so we can't actually use proportionality to find y, but because these are right triangles, we can use Pythagorean theorem. So we can say 9 squared plus 15 squared. I'm looking at these lengths here, 9 by 15, and that's going to correspond to y squared equals y squared. 9 squared, 81. 15 squared, 225 equals y squared. 306 equals y squared. And so then when we take the square root on each side to get rid of the square, we get that y is equal to the square of 306. What is that? 2 times 153. And that's 3 times 51, and that's 3 times 17. So I actually do end up with a pair here. A 3 gets out, the 2 and the 17 would stay under. So that's exactly 3 root 34 if we simplified it. With lengths, we don't usually do that. We usually approximate. So the square root of 306 is bigger than 17 but smaller than 18, but it seems roughly halfway in between. So I would say, well, that's probably about 17.5. Zoop! Oh my gosh, 17.49. I swear, guys, I don't look at these ahead of time. I just know them. All right, so you need to go ahead and work through, check your progress 2A and 2B to figure out those missing measures. So there you have it. That's my work for Check Your Progress 2A and 2B. Probably not the most rigorous work there. I skipped stating the similarity. The triangles did not have vertices labeled, and I didn't feel like doing it myself. But you should be able to tell pretty easily. In the case of Check Your Progress 2A, we must have three congruent angles across or three pairs of congruent angles across the two triangles. That demonstrates our similarity. Pretty clear relationship here from 9 to 27 multiplying by 3. And so we do the same thing for the other lengths there. 7 times 3 gets us B equals 21. 15 times 3 gets us A equals 45. In the other triangle, we have similarity, but not nice integer proportions. And so once we demonstrate the similarity, again, this angle down here has to be congruent to itself. Because we already have the right angles, these other two angles also must be congruent. And there you have it. That's our similarity. But from there, again, no integer proportions. And so instead, we have 5 over 7 equals x over 11. Cross multiply, divide by 7. And we get approximately 7.86. Exactly 7.85. 7142 repeating. 7 6/7, also known as. AKA. One more example. Let's knock this out. Janelle is standing near the Washington Monument in Washington, D.C. The shadow of the monument is 151.5 feet. That's amazing that she knows that. And Janelle's shadow is 1.5 feet. If Janelle is 5.5 feet tall, how tall is the monument? So this is actually, although it's kind of silly how we would know these things, this is how we can measure things that otherwise seem difficult to measure. In fact, is there... I guess maybe I'm thinking I've done this lesson with you guys before. We did a lesson on similar triangles last year because there's like a river problem where you're crossing a river and you're trying to find a given length. But anyway, not important. You can tell. I mean, they draw the triangles right in there for you. So then we have the Washington Monument, which, as everyone knows, is roughly the height of 3 people stacked on top of each other. No, just kidding. This is obviously not drawn to scale. We have an unknown height. We'll call it x. A classic. But we do know the shadow length is 151.5. I guess it is worth saying, obviously they've drawn these as similar triangles, but you might wonder, well, why are these similar triangles? Clearly we have the right angle, but where are the other angles coming from? And the answer is they're coming from Mr. Sun. Up here. He's the one casting both of these shadows, and so he's causing these angles to be the same because he's far enough away that he's not, they're not going to be different angles because of the position of the sun. So that's where the proportionality is coming from, or the similarness of the triangles is coming from. Obviously, we want to set up our proportions here. 5.5 over 1.5 must equal x over 151.5. And then from there, we want to do our cross multiplication. So 1.5 times x equals whatever on Earth. 5.5 times 151.5 is. We would then divide away the 1.5, divide away the 1.5. And I can tell, okay, so I have some decimal things going on here. And then maybe I can also say, well, 5 goes into this 3 times, goes into that 11 times. And so I end up with x equals whatever 11 times 151.5 is over 3. Turns out that, again, I have some cancellation here. This turns into 505 or 50.5 times 11. The 3 goes away entirely. And so finally I end up with x equals 555.5 feet, which is exactly what the book says for example 3. Take a moment, last part, workout check your progress number 3. All right, I'm just going to jump in here. A bit of a stretch here to call this a similar triangle problem. I guess maybe they want us to draw the tent with its height or something. I don't know. Doesn't really matter. Seems to me like it's more a straightforward proportion question. I've got my scale at the top here. 1 inch corresponds to 4.5 feet. Make sure to put inches over inches, feet over feet. And then we just want to go ahead and solve that. So 1 3/4 is the same thing as 7/4 equals, let's actually go ahead and call it 9/2. No, actually I don't think, yeah, I will. 9/2 is the same as 4.5 divided by, we'll call it x. We'll do our cross multiplication. X equals whatever 7/4 times 9/2 is, 63/8, 7.875. Don't forget your units, feet. So apparently this tent is actually, my gosh, what a gargantuan tent. Shaquille O'Neal could fit in that tent. So there it is. That's chapter 10. Hopefully you get a sense now of the scope of the chapter. We start looking at radicals and just how we deal with them as objects, how we simplify them, how we combine them, how we do operations with them, addition, subtraction, multiplication, and even a little bit of division, though we didn't talk about it that way. We called it simplification. We started with those so that we could then solve Pythagorean theorem style questions, because radicals end up in those Pythagorean theorem questions. Distance formula is the same as the Pythagorean theorem in the coordinate plane, so now we can do distance formula things. And then similar triangles, just because I guess we love right triangles. I don't know. So that part doesn't really fit in. But that's all of chapter 10. Go back, watch any videos on the lessons that aren't quite clicking, particularly before you complete the test, which is due on Friday, which is probably the day after you're watching this video, unless I'm in the future, in which case it's amazing here, guys.